Hi everyone, we're finishing up lesson 22 on the central limit theorem, the CLT, for means or averages. And finally, we're going to meet this theorem. We've seen them in bits and pieces, we've applied them in problems and examples. We're finally going to state the CLT for means. It's a lot. But basically, be aware of the assumptions and apply it when appropriate. The central limit theorem for means. Assume that X has some distribution D as the Big Daddy distribution. It was discrete uniform for one die. The mean is mu, the standard dev is sigma. That's the usual notation. We assume that sigma is finite, not infinite. Don't worry about that. So far, so good. The Big Daddy distribution is D, our old school notation. Mean mu, standard dev, sigma. So far, so good. Let X bar be the sample mean of n IID results from D, the Big Daddy distribution. Now, IID, these are three famous letters in probability theory. IID means independent and identically distributed. Independent in the sense that, let's say that you have a machine rolling 32 dice. The result on one die has no impact on the result of another die. They aren't magically connected by magic glue or anything. These dice are independent. And they're identically distributed. In particular, if you take each die has that flat Big Daddy distribution as the common identical distribution for all 32 dice. They all have distributions that are identical, the same distribution. Here I'm drawing a more generic picture. So of course, a die had a flat top. Here, we have a more messed up distribution, but this could still work for the central limit theorem. We could have n IID results from this distribution over here. Okay, so we have this Big Daddy distribution D, and we're drawing from it a sample of size little n. So for example, let's say we have dice, so we have the flat distribution. Let's say we have dice. We have a machine roll 32 dice. X sub 1 is the result of the red die. X sub 2 will be the result of the green die, and so forth. X sub 32 is the result of the orange die, whatever. The sample mean, X bar, is going to be the average of all these. As a random variable, basically it's telling us that whatever these 32 values will be, we'll add them up and divide by 32. But since the dice have not yet been rolled, right now X bar is a random variable. And it has a corresponding probability distribution. We don't know the value of X bar yet, but we can approximate its probability distribution by a normal distribution because of the CLT. All right, so here's our sample. It could be like 32 dice. There's our sample. We're curious about probabilities for the sample mean. Okay, now when can we apply the sample mean? If the sample size is large, in particular, n is greater than 30, the 30 comes from practical observation, not from formulas or algebra, or regardless of the size of the sample size, if you start off with a normal distribution, if Big Daddy D is a normal distribution, pretend that's normal, then the CLT applies regardless of the sample size. So if the sample size is big enough, bigger than 30, or if you start off with a normal distribution, then the CLT applies. And this normal distribution can be used to approximate the distribution for the sample means. And we can work out probabilities. According to the CLT, under one or both conditions, X bar has as its distribution, approximately, a normal distribution with this mean and this standard deviation or standard error. The mean, mu sub X bar, is simply mu, the mean of the Big Daddy distribution, D. The standard error, or the standard deviation of the X bar distribution, the standard error of the mean, is given not by sigma, not the standard dev of the Big Daddy distribution, but sigma over root n. The Big Daddy standard deviation divided by the square root of n. This is going to be smaller. As n increases, as the sample size increases, the standard error shrinks and we get tighter clustering about the mean. We saw this with the dice. Now, the CLT works best if you start off with a normal distribution. But just in general, when does the CLT tend to work better? And when do we need maybe smaller values of n as a requirement as opposed to really needing larger values of n, the sample size? In general, when does the CLT work well? Well, what are some properties of normal distributions? Well, they're symmetric and they don't have thick tails. In fact, normals fall off very fast. That's why we have almost everything within 2 or 3 standard deviations of a mean if you have a normal distribution. So even if you don't start out with a normal distribution, generally speaking, the central limit theorem tends to work better when we have at least a roughly symmetric distribution and something where the tails fall off rapidly. So we don't have something super lumpy like this on the edges. All right, so let's see how the central limit theorem does. Before, we had a standard die with a uniform distribution. What if we have a loaded die? Or maybe you have a die like this, where 3 of the faces are 1s, 2 of the faces are 2s, and 1 of the faces is a 3. Which means that the probability of getting a 1 is 1/2. The probability of getting a 2 is 1/3. The probability of getting a 3 is 1/6. This is not a uniform distribution. And the mean is not obtained by adding these up and dividing by 3. You have to use the zigzag. This times this, plus this times this, plus this times this. The mean is about 1.7. It's biased more towards the 1 as opposed to the 3 because a 1 is much more likely than a 3. The standard dev is about 0.75. Again, we didn't cover that calculation before, but take that on faith. All right, so for one die, here's a straight up spike plot for the original Big Daddy distribution. 1/2 mass for 1, 1/3 mass for 2, 1/6 probability mass for 3. That's a spike plot for n equals 1. For n equals 2, what if we take the average of these 2 weird dice? We get this spike plot. N equals 4. N equals 8, n equals 16, n equals 32. Now, by the time we get past 30, look at this. The distribution of sample means is very normal, and there's a tight clustering about 1.67, the Big Daddy mean. And that was the case even though this was not normal, not uniform. It wasn't as good as a uniform in the sense that it's not symmetric. So unlike a normal curve, and unlike the uniform distributions for the dice, this year, this is not symmetric. So we had to wait longer. We had to wait a bit longer for us to get that bell shape. Okay, before there was a marked skewness to the right. All right, and the CLT would apply. These are the new parameters. All right. And again, if you had a distribution that was very asymmetric or something that was very lumpy on the edges, then it might take a while. It might look pretty messed up for n equals 4, n equals 8, very far from normal. But even for a messed up distribution like this, by the time you got to n equals 32, the result will be fairly normal. Even for a messed up distribution like that. Actually, I apologize. It is kind of symmetric, but the problem is it's very lumpy in the tails. Right. Maybe something that's even more messed up might be something like this, where it's like maybe this here, that there, where it's asymmetric and kind of lumpy tails. Okay, so that is the central limit theorem for means. Next time, we're going to talk about another application of normal distributions, approximating our old friends, the binomials from before. And that's next time.